still grabbing their last cups of coffee. I think we stopped off with balance. So when we speak about the energy waste, when we speak about the electrical waste that happens, you've got the harmonic side, you've got voltage imbalances. These are very common quantifiable methods of waste. This is how you know that you have waste there, reactive power as well. But what's important to understand is besides all these losses, okay, besides losses in harmonics, unbalance, etc., we have a very important loss that we call cable losses. This is where all the other losses happen. We call cable losses. So again, formula of I squared RT, depending on the length of the cable, the diameter of the cable, you will have a quantifiable loss. So typically what happens is we have customers that hire consultants to measure energy waste. And this is how it's been done till we had some meters with us. But you know, companies would hire consultants and say, listen, please come to our plant and identify the energy waste for us. So they would measure unbalance, they would measure harmonics, they would look at the reactive power. But then to give you an idea of what the exact losses are, it's very important to know the cable losses, right? If you, a 100-meter cable as opposed to a 50-meter cable will have a different loss value. Remember, it's heat loss, I squared R. So as that resistance increases, you have different associated losses. What's nice with our new 435 Series 2 power quality meter is that this meter can automatically measure that loss. We can measure cable loss. And that's with our energy loss calculator. So where to measure with the Fluke 435-2? Again, on the input side, you want to measure on the input side. And what we have is this patented energy loss calculator. This is a function that is not available on any product worldwide. There's no other company that has such a calculation built into a product. It's patented by Fluke, and that's why it's very good, because this is the true energy loss that you have. What the 435 Series 2 will do is it will tell you what is your effective kilowatts. This is the amount of energy that you actually have that you can use. But you have some losses there because of I squared R, cable losses. It also measures the reactive, the unusable power. It also tells you the distorted power, the unbalanced power, and the neutral current. How much of neutral current do you have? Because if you have high neutral currents, that's also lost. This cost factor here, at the end of the day, it tells you, because of all these problems, I am losing 23,000 euros a year in wasted power. Right? This calculation, this was done by consultants before, by our meters itself. They would take the measurements, but they would go back, a month and a half later, they would come back with a projection. What we have done is we have put that entire calculation inside the meter. So now you only pay half the price that you would pay, not even half, you would pay a fraction of the price you would pay to a consultant, but you have the costing inside the meter. Important things that you want to enter: length of the cable, diameter of the cable, and most importantly, how much you are paying per kilowatt hour. And you can change this to euros, to dollars, to dirhams, whatever you want. The currency is not a problem. Okay? So understand this, because this is a unique feature that's only available on a Fluke tool. There's no other manufacturer that has this patented loss. Okay? So this is you're looking at thousands and thousands of algorithms that actually define this costing analysis, but it's a very effective tool, and it's actually helped a lot of customers find out what the energy loss is. Okay? So this will give you a good snapshot. So if you want to find out, okay, what's my system looking like, I connect this on the main, and I see, do I have extra reactive power, do I have high harmonics, and then I go to the individual loads and measure each parameter. This is also a very good tool to understand where do I move next? What's the next step? What do I have to do? If I don't have any capacitor banks or no harmonic filtering, this is a good step to tell me what do I need to do. For example, here I can see that my biggest loss is in my true power. Okay, my harmonics and everything is fine, but my biggest loss is in true power, cable loss, so I might need to cut down on the cables, cut some of the cable length. If my loss like here, 1.6 euros, I'm getting for distortion, that means I'll have harmonics, so I might need to install harmonic filtering. Or if it's high reactive power, I might need to install capacitor banks. So it's a good mitigation step. Okay, so unique and patented, it's only on the 4352. You can have a look at it, of course, later on. So that's on the utility side. Now we move into the next part of the building, which is the production. Okay, so you've got the utility, you've got production sub-process, and you've got building envelope. So in the production process subsystem, we are talking about mechanical loads, we are talking about HVAC, but also airflow, compression, compressors, steam systems. So electromechanical loads. This is an example of an electromechanical load. Okay, you've got a motor that's driving, let's say, a pump, and this motor is of course driven by a variable frequency drive. So every measurement on the input side of the drive can be done with a power quality meter. The harmonics, unbalance, distortions, etc. can be measured here. On the output side of the drive, how it controls the motor. On the motor side, you can also measure the temperature, right? Contacts. A lot of times you want to measure the motor terminals. If you look at a hot spot in the motor terminal, that's usually because of excessive vibration. Makes the motor termination come loose. You want to measure the insulation life of the winding of the motor, right? If the insulation fails, the motor is going to generate a lot of heat. Unbalance, voltage unbalance. Like I said, motors do not like to see more than 2% voltage unbalance. Anything higher than 2%, very bad for a motor. Temperature, vibration on the coupling and on the driven component, on the pump side and so forth, bearing temperatures, all indicators of energy waste. So, temperature measurement. Next best thing, right? The second most parameter next to time. Temperature is a very good indication of a problem. And in mechanical devices, temperature is giving you signs of bad cooling because of bad airflow. The motor airflow is not good. Bearing problems, if the bearings are going bad, friction increases. Friction is manifested as heat. Temperature increases. Bad alignment. If you have bad alignment of the shafts, that also causes heat to come up. Electrical, connections, etc. Normal motor, bad motor. Both these motors are driving the same load, same conditions, but they have different temperatures. You don't need to be an expert to know that there's a problem there, right? If you have two systems exactly identical, exact same loading, if one of them's got an extreme temperature, something is definitely wrong. And the good thing is when you measure, again, like I said, with thermal imaging, you are measuring the surface temperature. But measuring the surface temperature gives you a very good indication of the internal winding temperatures. And typically, if your maximum temperature, surface temperature, is increased by 10 degrees more than what the motor is specified for, I have immediately lost 50% of my insulation. So if the motor is rated at 40 degrees, every motor on the nameplate will have an operator's temperature. If you're measuring 10 degrees more than that, guaranteed you've lost 50%. Because if the surface of the motor is reading 80 degrees, and mind you, you are reading the surface, okay? Between the surface and the winding, there's a lot of gap there. What you're reading 90 degrees here might be 120, 130 degrees on the winding. So it's typically 20 degrees cooler than the winding temperature. So you want to reduce that temperature, of course, but again, very good indication of insulation life. So we do have a 5-point thermal inspection, okay? And I'll show you a little video because I have my colleague explain that to you. Find that one, there we go.
Hello, my name is Michael Stewart with Fluke Thermography. Today we're going to use thermal imaging to inspect a common electrical motor for issues that might be impacting energy usage. So, done a little bit of prep work. We'll show you what we've done when we get over there. First thing you always need to have is proper equipment. Make sure you have a thermal imager, it's powered up, ready to go. Make sure you have proper personal protective equipment. Here we have an electrical motor coupled to a pump. The work that we've done in advance, obviously you can see that we've removed the shroud over the coupling and we've removed the cover over the junction box, the termination box. Need to have direct line of sight with thermal imaging in order to do a proper inspection. The first thing that I generally like to do is I'll take a look at the overall motor, the housing itself, and I'll be looking for unusual hotspots or localized hotspots that I wouldn't expect. In a normally operating motor, you would expect nice, even heating and distribution across the entire housing of the motor. If you see anything that's off, that could be indicative of a problem. Likewise, if we look at this motor and it's running a lot hotter altogether over the entire motor housing, that's an issue as well. So let's take a look first and see what we find out. Looks quite even. I don't see any issues there. You know, obviously, if this motor were running hotter than usual, that could be an indication that perhaps the cooling fan's not working properly, it's not aspirating properly. I think everything's working okay here. Number one, the temperature is good. Number two, the fan is operating. If I do find a localized hotspot, that could be indicative of a problem with one of the phases. Maybe some of the windings are burning out. Too much heat will destroy that insulation. Could also be an issue with transients on the line. Could be a problem with harmonics on the line, causing unusual heating. Either one of these situations, the overall overheating or the localized overheating, can cause that motor to work a little bit harder than it needs to. It will draw more current in order to compensate for the problems that it has, and that will impact your bottom line and your energy usage. Next thing that I'll move on to is the electrical itself here in the termination box. I'll look for high resistance connections. So I'm not seeing anything here, but if I were to see a high resistance connection, could be too loose, too tight, strands broken on the line, something like that. That will dissipate some of the electrical energy you want to actually make the motor work, and it will dissipate it as heat, as waste heat. And it might not be a whole lot every year, but those kind of connections add up, so definitely take a look at those. Also looking to see if there's any overload situation on any of the lines. I'm not seeing anything there. You know, a single phasing motor may be operational and may be working, but you're going to see two of the phases significantly warmer than the one that was shut out, okay? It'll be a lot cooler, and that motor will start overheating. It will actually draw more power just to try to keep running. So definitely look out for things like that. No issues there. I'm going to come up here now and we're going to take a look at the mechanical portion of the motor, the bearings. So once again, we're looking at the shaft end of the motor, and I don't see any issues. If I were to see an issue here with this particular bearing, it would be warmer than the rest of the housing. Usually, if something is 5 to 10 degrees centigrade above the temperature of the main part of the housing and it's on a bearing area, something's going on with that bearing. You need to do some extra work to try to figure out what's happening, because a misalignment, a bearing that's just wearing out, over lubrication, under lubrication, all of these things can also cause that motor and this motor pump assembly to operate inefficiently, draw more power, and not actually get the work done that you want it to do. So everything looks fine there, not seeing any issues. All right, you have to be a little bit careful when you're taking a look at couplings and shafts and things like that, because they tend to be a shinier metal, a lower emissivity material. So sometimes you can get reflections off of them that aren't really there and aren't indicative of the actual heat. In this case, I'm not seeing too much going on. I see a little bit of extra heating around, on the motor side of the coupling, but that could be an emissivity issue. I don't really know at this point. I'm not seeing anything significant. And because I'm not seeing any excessive heating on the bearing of the motor itself, tells me that more than likely the alignment's probably pretty good on here. So we're now going and going to take a look at the pump side of the pump. Don't see any issues here. I think this is operating really well. Any of these problems that I've discussed before is a great opportunity to say, okay, well, what do I do next? I've discovered something that may be draining energy, draining money out of my budget. How do we fix it? Well, you have to be able to diagnose it. So a lot of things, if you're finding a problem with the thermal imager, and it looks like it's a bearing related or coupling related, you can then use a vibration tester. From an electrical standpoint, you find a high resistance connection or something that looks like it might be overloaded, you can use a clamp meter. If you're finding problems that are localized hotspots, it might be a problem with internal windings, it's a good opportunity to use the power quality meter. It could be, as I said, transients, harmonics, anything like that. All of these tools work together in conjunction to help you better maintain your equipment and save energy over the long run. I hope this was helpful to you. As you can see, it's not rocket science. Anybody can do this. You can start saving money and frustration today.
Okay. So, nice little video to show you a typical 5-point thermal inspection. And again, like Michael clearly says in the video, sometimes you need more than one tool to do it. So if you have overall heating on the motor, you might want to install a power quality tool to see what's wrong. If the camera is showing you bad alignment, you want to verify that by using a vibration tester as well. But thermal imaging is a very easy tool to use. It's quick and intuitive, and it gives you an answer on the spot. But we also have another option, which is our VTO2. This is a visual IR thermometer. Okay, so this is something that is much more lower end. It's not a thermal imaging camera. It's a thermometer, but it's a visual thermometer because you can visually see the spot that you're measuring. Unlike a normal thermometer that only shows you a number. So it's the convenience of a normal thermometer with the visual advantage that you only get on a thermal imaging camera. So it's sort of the best of both worlds. It makes it easy to find hot and cold spots. If you look at the same motor picture, you can see that the thermal image it's not really a thermal image because the clarity is absolute, it's nothing, it's really bad. But it shows you a good heating pattern. And that's what you want to see on the field, is that heating pattern. So this is sort of a good technician level tool that you can go and check easily all your motors and stuff. And once you find a problem, you can bring in the thermal imaging camera to look at it in much more detail. Okay? So that's the visual thermometer. Again, this is new and unique from Fluke because it's a new tool category, and there's no other company that has such a visual thermometer. Everybody's got either a thermometer or a thermal imaging camera. There's nothing in between. This product is really something in between. So calculating electromechanical waste, we have seen with our 4352 with the energy loss calculator, you do get a very good idea about the wastage, how much you are wasting every year. But you should use this as a means to do corrective actions and to justify the ROI. It's the money that you're spending for the fix. It's a good calculation there. So looking at things like high resistance, overloading, off-design voltages, harmonics, single phasing on motors. Now if a motor is single phasing, the chances are it's still running, but it's going to be a lot more hotter because you have two phases that are at a higher temperature than the one that's cut off. Electromechanical friction waste. So again, we spoke about friction and that or mechanical energy that's manifested into heat. So friction-based inefficiencies is energy waste. So alignment issues, bearing wear, structural looseness, foundation looseness, etc. All problems. Alignments, a perfect alignment occurs when the center line of two shafts coincide. That's when you have perfect alignment. If one of them is off, you've got friction there. Bearings carry the most load in a mechanical device. And these are the most common failures in mechanical devices as well. So bearings, you want to make sure that they're good. Imbalance, it occurs when you have a heavy spot around the shaft. And looseness is either looseness between the foundation and the motor housing, or within the motor, within the bearings, you've got structural we call it rotating loosens as well. So the Fluke vibration tester is very useful to do mechanical devices because it tells you the problem on the spot. It tells you, it tells you what the problem is, it tells you where the problem is, and it tells you how bad the problem is. So this gives you a good predictive maintenance approach because you know exactly, okay, do I take this machine down today or do I have a month or two to keep it running and I can really fix it only when it needs to be fixed. And that's the condition that you get with our vibration tester. So which is better, thermal or vibration? As Fluke, I'd say both, right? Because then you buy 2 units for money. But of course, it's you have to look at it this way. If you look at let's start from the back, okay? Just before a mechanical device fails, contact heat, it's extremely hot. You cannot touch the motor. Okay, that's a sign that says this guy is done. Just before that, audible noise. You start to hear that the motor is really crying for help. Before the noise, thermography, right? Before thermography, oil analysis will show you lubrication problems. And before that, you have vibration. So if you look at the curve, vibration is the first indication of a mechanical problem. And you are talking 1 to 9 months from start of problem till the fail. Thermal imaging, 3 to 12 weeks. So by the time a thermal camera picks up a hotspot, you've already lost 70% of that motor's life. It's almost towards its end, right? So changes in vibration is much better. So vibration is the best tool there is to look at mechanical devices. The problem, however, vibration is not easy. It's a lot more complicated. You need to be an expert in vibration. You need to understand how to read the spectrum, etc. But thankfully, Fluke is a lot more useful because the Fluke 810 is the expert in the field. And this is really designed for people like you that are in maintenance and want quick answers. You don't want to wait for consultants to tell you what's wrong. You want a cheap and simple unit that does the work for you, that gives you the answer on the spot, that you can rely on. And that's what the Fluke 810 does. So the 810 works in 3 simple ways. The first step is to set it up. You tell the instrument what are you measuring on the field. A motor which is coupled to a compressor, gearbox, whatever it is. You build the setup in, you take the measurements, and then you push the 3rd yellow button on site. It tells you what the problem is. With typical data collection units, you would take the measurement on the site. You would either have to go back into the office, feed it into a software program to tell you the answer, or the consultant has to analyze the data. We provide the answer on the spot. So you know exactly at that point, okay, what's the condition of this device? How long do I have before it fails? So we will focus on the 4 biggest faults that you have in mechanical systems: imbalance, looseness, bearing wear, and the misalignment. Slight, moderate, serious, and extreme condition, and this is a traffic light indication, so you know red meaning stop, green means okay, I can still run, yellow and orange meaning okay, problems are happening, I need to be, let's say for example you find a motor and it's on the green, slight indication of vibration, you can still keep it running. You can do your regular maintenance, which might be every 1 month you take a reading, and then in the 3rd month you see that it's jumped from green to yellow to orange. Now you want to think, okay, maybe I need to reduce my maintenance time, so instead of 1 month, I take 1 week measurements. It gets to red, hey, this is the time I need to stop this now and do corrective maintenance on that. So it gives you a good plan ahead time. Again, comes with the software, free of cost, license free. Okay, so it's a complete package. The unit, the sensor, the whole thing comes in one package. It's a very good vibration tester. Let's look at compressed air. Also a big indicator of energy waste. Again, if you look at compressed air systems, you've got electrical panels that drive the compressor, of course, giving it the power. So here, on the panel side, you want to measure things like harmonics and balance and so forth. On the compressor itself, This is compressing the air. You want to measure the pressure output because pressure is a good indication of leaks, right? You want to measure the pressure. Pipes involved, steam traps, you can measure for leaks using thermal imaging cameras. And then on the pneumatic tools, whatever pneumatic systems you have, again, you want to measure the pressure drop because that will give you an indication of leaks as well. So primary waste sources, common inefficiencies, you have leaks, blockages, shaft misalignments on the compressor as well. Vibration is another example. And when it comes to pressure, the most common leaks you always find on the connections. Hoses, connections, sealings. If you don't have proper sealants, you always have bad leaks. So waste points, like an example here, you can see a bad regulator, quick disconnects, air wall, there's no pipe sealants, there's no sealant across the pipes. That also gives you a sign of energy waste. Because if you don't have any sealings between connections, you've got gaps there, air gaps that will basically leak out air, and you want to be able to measure that. So compressed air inefficiencies, very useful information. 5% of the total energy consumed by compressors is actually converted into compressed air. Just 5%. The rest, 95% of energy, is transformed into mechanical, heat, and noise. Right? And that's what you want to see. So between 20 and 30% of the compressor's output is often lost via air leaks. And you want to capture these air leaks because those are expensive. So energy flow in the compressor, if you put 100% electric energy into the compressor, 5% is actually used to transform that energy into compressed air. The rest, 95%, is heat loss. Radiation out into the atmosphere, friction, etc., and so forth. So you want to make sure that you measure all these compressors. A very good tool, thermal imaging, clearly identifying, like in this case, compressor, you can see one of the piston heads are hot, then the other ones indicating you have a problem with this compressor. So thermal inspections you want to do